We're about to explore one of the most famous, most important, and honestly, one of the most brain melting experiments in all of science. It's a story that pits these absolute titans, like Einstein and Bohr, against each other and makes us question what reality even is. And it all starts with this one question that sounds so simple, but is actually kind of impossible. Is light a particle, like a tiny bullet, or is it a wave, like a ripple spreading across a pond? This question, it's the key that unlocks the entire quantum world. Now, before things get super weird, let's just ground ourselves in what common sense tells us. In our world, the world we see every day, things are one or the other. A baseball is a particle. It's in one spot at one time. A ripple in a lake is a wave. It's spread out. They're just completely different things. Okay, so the first major clue in this whole scientific mystery comes from an experiment that's just beautiful in its simplicity. It was first done over 200 years ago, and it still messes with physicists' heads today. This is where our common sense just starts to completely fall apart. For the longest time, the debate was pretty one-sided. You had the great Isaac Newton himself, and he was a huge believer that light was made of these tiny little particles he called corpuscles. But then, back in 1801, this guy named Thomas Young decided to actually test it. And what he found, well, it changed everything. And what's so wild is just how simple this whole setup is. All you need is a light, a wall with two little slits in it, and a screen behind that to see what happens. That's literally it. So, given that setup, what would you expect to see? Well, if light is just a bunch of tiny baseballs, or corpuscles, like Newton thought, the answer is pretty obvious. The ones that go through the left slit hit here. The ones that go through the right slit hit there. You should just get two bright lines on the screen. Easy, right? But that is not what they saw. Not even close. What they actually saw was this: a whole bunch of bright and dark bands. It's called an interference pattern, and it's the signature of a wave. It's exactly what happens when two waves in a pond overlap. So light's a wave. Case closed, right? Nope. This is where the story goes from just a mystery to full-on weirdness. So scientists thought, okay, let's get clever. We'll fire the little light particles, the photons, one by one. And we'll stick a little detector right by the slits to see which one each photon actually goes through. And this is the absolute kicker. The second you watch to see which path the photon takes, that whole wave pattern, it just vanishes. Gone. You're right back to seeing two simple bands, just like you'd expect from particles. It's almost like the light knows you're looking and changes how it acts. The simple act of measuring it forces it to behave like a particle. This one absolutely bizarre result, it kicked off one of the greatest debates in the history of science. It put two of the biggest minds on the planet, Albert Einstein and Niels Bohr, head-to-head over the very nature of reality itself. So you basically had two camps. In one corner, you've got Einstein, the realist. He just couldn't stomach this. His take was, look, the particle obviously went through one slit or the other. We just don't have a good enough theory yet. But in the other corner was Bohr, and his view was way stranger. He said, nope, before you measured it, the particle wasn't in any single place. The measurement itself helped create its position. This diagram really gets to the heart of it. The whole debate is about what's going on before we look. Was the particle always at some specific point, like the realists thought, and we just found it? Or was the particle in some fuzzy state of possibility, and our measurement forced it to suddenly appear right there at that one spot? Einstein he was convinced there had to be a loophole. He came up with these brilliant thought experiments. He was like, what if we use a screen on really sensitive springs? We could tell which slit the photon went through by measuring the tiniest little recoil without ever looking at it. We could beat the system. But Niels Bohr had the ultimate comeback, and it was a core rule of quantum mechanics itself, Heisenberg's uncertainty principle. All this really says is that there's a fundamental trade-off in the universe. You can't know a particle's exact position and its exact momentum at the same time. The more you know about one, the less you know about the other. And here is where Bohr just brilliantly checkmated Einstein's idea. He showed that for those springs to be sensitive enough to detect the photon's recoil, the screen's own position would have to become so uncertain, so fuzzy, that it would completely smear away the interference pattern. You could never ever get that which path information for free. Okay, so let's fast forward to today, because this century-old argument was just recently put to the ultimate test. A team at MIT performed what might be the most perfect version of this experiment that anyone's ever designed. So instead of some metal plate with slits, they used a cloud of over 10,000 individual atoms. This gave them a level of control that scientists 100 years ago could only dream of. And they got that control by cooling these atoms down to temperatures that are just mind-bogglingly cold. We're talking microkelvins, a tiny, tiny fraction of a degree above absolute zero, the coldest temperature possible. At that point, you can use lasers to arrange them into a perfect crystal. So, in this amazing setup, light wasn't passing through slits cut in a wall. It was passing through the gaps between the atoms themselves. Like the head of the team, Wolfgang Ketterle, said, these atoms were basically the smallest slits you could possibly build. But here's the really brilliant part. They could use their lasers to change how tightly they held onto the atoms, which basically let them control how fuzzy the atoms' positions were. This meant they could tune, with incredible precision, exactly how much witch path information was leaking out into the world. So, after a century of arguments, all the thought experiments, and now this incredibly precise modern test, what was the final verdict on how reality works? Well, the results were just undeniable. They lined up perfectly with the predictions of quantum theory. It wasn't about some physical kick or jiggle, it was all about the quantum fuzziness. The more information you could get about the path, the weaker the interference pattern got, exactly like Bohr had argued all those years ago. And what that means is, look, Einstein was an absolute genius. Nobody's questioning that. But on this one specific, really deep question about reality, it really looks like he was wrong. The dream of secretly finding out which path a particle took without destroying its wave nature just seems to be fundamentally impossible. Which leaves us with this one last, absolutely staggering question. If our observation isn't just seeing reality, but is actually helping create it, then what on earth is the universe doing when nobody is looking? It's a mind-bending mystery, but it's also a practical one, because it's by learning to control this exact weirdness that we're now building things like quantum computers. The universe's strangest secret might just turn out to be its most powerful tool.
Arguably the most famous and definitely the most baffling idea in all of physics.
The mystery of quantum measurement.
Exactly. We're talking about why reality itself seems to change, depending on whether or not we're looking at it.
It's the core paradox. For, almost a century now, we've known that a quantum object, a photon, an electron, it behaves like this spread-out wave, a wave of probability.
Until you measure it.
Right. The exact moment we try to pin it down, that whole wave just instantly snaps into a single definite particle, one spot.
And that snap is called the collapse of the wave function. It's the heart of what physicists call the measurement problem. We've pulled together some really great sources for this deep dive, everything from, foundational physics text to some very lively online debates.
And crucially, reports on a new ultra-precise experiment, an idealized experiment, they're calling it, from MIT.
So our mission today is to get a handle on this. We want to understand what the wave function collapse actually is, why it's such a philosophical headache for physicists, and, this is the exciting part, how this brand new experiment seems to have finally settled a huge argument.
A nearly century-old debate between two titans of the field, Albert Einstein and Niels Bohr.
Okay, let's unpack this. Let's start with the basics. This fuzzy reality, the math behind it. What exactly is this wave function, this psi symbol we always see?
Well, the first thing to remember is the wave function isn't the particle itself. It's more like a mathematical description of a cloud of possibility, a map of potentiality.
So before you look, the particle doesn't have a specific location.
It doesn't. It exists in a state we call superposition, which means it kind of holds all those potential positions at the same time.
So it's not that we just don't know where it is, it's that it literally is in all those places at once.
Precisely. And to make that useful, we use something called the Born statistical interpretation. It's a rule.
A rule that says what?
It says if you take the wave function at any point, square its magnitude, what you get is the probability of finding the particle right there at that moment. It's a prediction engine for outcomes, not a direct photo of reality.
Okay, so the wave function gives us a menu of possibilities, but then we actually do the measurement. Let's say for particle spin, you have a mix of up and down states.
Right. Mathematically, that's something like op wrangle plus b down wrangle.
And when we measure it, that whole equation just instantly becomes either up wrangle or down wrangle, one or the other. Why is that collapse so so problematic?
That is the crux of the problem. Because the standard approach, the Copenhagen interpretation, it forces you to use two completely different rules for how the universe works.
Two different rules.
Yes. Rule one is the Schrödinger equation. It says systems evolve smoothly, continuously, predictably. But then you have rule number two, the measurement rule.
Which says?
It says when a measurement happens, all that smooth evolution just stops. The system instantly, discontinuously collapses into one outcome.
It sounds like we're saying nature runs on this beautiful, smooth equation until we look at it. Then it panics.
Exactly. And that's just, well, it's philosophically messy. Quantum mechanics is supposed to be universal. It should apply to everything. Electrons, atoms, us, planets. So why does the act of measurement get its own special, separate rule?
It doesn't define the boundary, does it? Where the quantum world stops and our classical world begins.
It doesn't. And that philosophical looseness, that's what drove Erwin Schrödinger to come up with his famous cat thought experiment. He wasn't trying to say a cat could be alive and dead.
He was making a point.
He was trying to show how absurd this boundary was. He scaled up the quantum weirdness to our world. If an atom can be in a superposition of decayed and not decayed, and that atom is linked to a vial of poison,
then the cat is also in a superposition of alive and dead until someone opens the box.
Right. The math forces you into that conclusion because the theory gives you no clear line for where or when that collapse is supposed to happen.
Which brings us to the ultimate arena for this whole debate.
Yeah.
The double slit experiment.
The classic. 2 centuries ago, Thomas Young showed that light passing through 2 slits makes an interference pattern. Proof that it's a wave.
But then if you put detectors at the slits to see which one the light goes through,
the interference pattern just vanishes. Gone. The light instantly stops acting like a wave and starts behaving like a stream of particles. You just get 2 spots on the screen behind the slits.
the very act of getting that which path information forces the collapse.
It does. And this wave-particle duality, it set the stage for one of the greatest friendly rivalries in science history.
Albert Einstein versus Niels Bohr, starting back around 1927. Einstein just hated this. He was a realist. He believed the particle had to have a definite path, whether we looked or not.
He couldn't accept that reality was somehow created by observation. So he came up with this brilliant counter-argument, a thought experiment, the spring slit.
The spring slit, right? What was the idea?
He argued that if you mounted the entire slit screen on incredibly sensitive springs, you could detect the tiny recoil, the little push from the particle as it went through one slit or the other.
So you'd know its path, its particle nature.
Exactly. And his challenge to Bohr was, can you get that particle path information without disturbing the system so much that you destroy the wave's interference pattern? If you could do both, you'd prove Bohr's idea of complementarity was wrong.
That's such a clever way of thinking. But Bohr, he had an answer, didn't he?
He did. Bohr used quantum mechanics' own ultimate defense mechanism against Einstein, the Heisenberg uncertainty principle.
Of course. You can't know a particle's position and its momentum with perfect accuracy at the same time.
Right. And Bohr showed that if you tried to measure the recoil of the spring precisely enough to know which slit the particle went through, that very measurement would introduce an unavoidable uncertainty in the position of the slit itself.
So trying to measure the momentum precisely makes the position fuzzy.
Exactly. And that fuzziness in the slit's position would be just large enough mathematically to completely smear out and erase the delicate interference pattern. So Bohr's point was that complementarity, this idea that you can't see both wave and particle at once, isn't a limit of our technology. It's a fundamental, unbreakable law of nature.
He effectively beat Einstein at his own game, using the rules of physics.
On every single thought experiment Einstein proposed, yes.
Okay, before we get to the new experiment that actually tested this, we have to clear something up. A huge misconception we saw in all the sources.
The consciousness myth.
Yes. When we say observer effect, people often think that means a conscious human mind is somehow involved.
It's the single biggest misunderstanding. The sources are absolutely clear on this. The observer in quantum mechanics has nothing to do with consciousness or a human brain. Observation is just a physical interaction.
So it's the energy, the photon you bounce off the electron to see it, that causes the change, not the fact that a person is aware of it.
Exactly. Any interaction that extracts information about the particle's properties, like which slit it went through, changes the system's state. Richard Feynman had a great line about this.
What was that?
He said, nature behaves the way she is going to behave whether you bother to take down the data or not. The measurement is the physical event.
Right. So the big question that lingered for a century was, okay, maybe Einstein could have been right if we just had better technology, a more sensitive setup.
And that's what makes this new MIT work so remarkable. In 2025, they essentially built the most perfect, idealized version of Einstein's spring slit experiment you could possibly imagine.
So how did they do it? What were the slits?
It was incredible quantum engineering. They took over 10,000 rubidium atoms, cooled them down to microkelvin temperatures, so just a sliver above absolute zero, and held them in a crystal-like lattice using laser light.
And the slits were.
Two adjacent atoms. They isolated two neighboring atoms to act as the physical slits. I mean, you can't get smaller or more controlled than that.
And the laser light holding them in place, that acted as Einstein's springs, right?
That's the beautiful part. It holds the atoms in place, but allows them to recoil if a particle interacts with them. So they had total control. They could adjust the fuzziness of the atoms' positions.
And by adjusting the fuzziness, they controlled how much path information they could get.
Precisely. They could measure the trade-off in real time.
So what did they find?
The results were crystal clear. They lined up perfectly with the quantum predictions. The more path information they could get, which meant the atoms were more localized, less fuzzy, the more the wave interference pattern washed out. A perfect, quantifiable trade-off.
And they settled the spring part of Einstein's idea for good.
They did. They showed the interference faded simply due to the intrinsic quantum uncertainty of the atoms themselves. It wasn't about the measuring device. It confirmed Bohr's counterargument completely. The interaction required to know the path inevitably diminishes the wave nature.
So Einstein, in this particular challenge at least, was definitively wrong.
He was.
Here's where it gets really interesting, though. We've confirmed the math works flawlessly, but that philosophical problem of the collapse is still there. So what if we could just get rid of it?
This is where we get into the different interpretations that try to do just that. They try to save that smooth, continuous Schrödinger equation from being interrupted.
And the first major contender is an idea called decoherence.
Right. Decoherence doesn't really eliminate the collapse, but it explains it away. It makes it seem like it happened, when maybe it didn't, not really.
How does that work?
The idea is that no quantum system is ever truly isolated. It's always interacting with its environment, air, molecules, photons, everything.
Okay.
So when a system is in a superposition, that interaction causes its quantum coherence to leak out and become entangled with the entire environment, rapidly and irreversibly.
So the system never actually collapses to one state. It just gets so tangled up with the outside world that for all practical purposes, the wave-like possibilities are lost. It just looks like it collapsed.
Exactly. Decoherence explains why our world looks classical, but critics say it doesn't fully solve the problem. It just sort of kicks the can down the road. The superposition still exists in the math, it's just bigger now. It includes the cat, the box, and you.
Which brings us to the most radical, most mind-bending solution of all, the many-worlds interpretation.
MWI.
MWI takes the boldest step. It just eliminates collapse entirely. It says the Schrödinger equation is the only rule, period.
So when a measurement happens, what does it say is going on?
It says the universe doesn't choose an outcome. It branches. It splits into multiple non-interfering realities. So in one new universe, you see the particle spin is up. In another, a copy of you sees the spin is down. Both happen.
That neatly solves the collapse problem. Nothing ever collapses, but wow, what a price to pay.
The price is what they call ontological extravagance. You're creating an infinite number of universes every moment. But the deeper problem, the one our source is really focused on, is about probability. Right, if every single outcome is guaranteed to happen in some world, then why do the probabilities in the wave function even matter? Why does it feel like a 90% chance is more likely than a 10% chance?
That's the probability problem of MWI. If everything happens, what do the numbers even mean? Proponents have tried to find ways to get probability back through ideas about counting worlds or subjective uncertainty, but, well, it's the main sticking point for many physicists.
So after all this, what does this all mean? The MIT experiment confirms Bohr was right. The math of quantum mechanics is perfect.
It is. The theory works. It predicts outcomes with unbelievable precision. The debate that's left is entirely about the nature of reality itself.
It's metaphysics.
Exactly. This isn't religion, it's philosophy grounded in physics. Whether the wave function collapse is a real physical event or just something that seems to happen because of decoherence or splitting worlds, that is still a completely open question.
That's the key takeaway. Now, as we finish up, I want to leave you with one last provocative thought. It connects this idea of collapse and reality. And it comes from something our sources mentioned. John Bell.
Ah, Bell's theorem, one of the most important results in modern physics.
Absolutely. Bell showed that any theory based on what he called local hidden variables.
Which is the classical realist idea, the idea Einstein held that a particle always has a definite location, we just don't know it until we measure it.
Right. Bell proved that those kinds of theories are mathematically inconsistent with the predictions of quantum mechanics. And since experiment after experiment confirms quantum mechanics,
It forces us to accept that nature is fundamentally non-local.
this is a huge concept. What does non-locality mean?
It means that if you have two entangled particles and you measure one at point A, forcing its wave function to collapse, the state of the other particle at a distant point B is correlated instantaneously, faster than light.
Okay, so here's the thought for you to chew on. If the observer effect isn't about human consciousness, but it is about this instantaneous non-local connection that links distant parts of a system the moment a measurement happens, what does that imply about the interconnectedness of knowledge and reality? An interconnectedness that we have yet to truly grasp. Think about the speed of light being the ultimate speed limit, and then think about reality connecting with itself instantly across the entire universe, something for you to ponder.